Hey everyone, and welcome to another deep dive. Today we're going to be talking about something that you probably don't think about that much, but it's actually pretty fascinating when you get down to it. We're going to be talking about gelation.
Gelation.
Yeah, so we're working with some excerpts from a textbook on polymer chemistry, and we've got a couple of helpful diagrams as well.
hmm
And we're going to try to explain what gelation is, how it works, and where we see it in our everyday lives. You probably encounter it more often than you realize.
Yeah, it's funny because most people, when they think about gelation, they just think about something getting thicker. But actually, what's really interesting about gelation is that it represents kind of a fundamental change in the way a material is connected. So I think a good analogy might be like, imagine you're in a room, just a big room full of people, and they're all kind of mingling around. And that's your liquid, right?
Mm.
But then suddenly everybody reaches out and grabs the hands of the people around them, and you get this kind of, network forming. And that shift, that is basically what happens at a molecular level when something gels.
So are those handshakes, are those the polymers?
Exactly.
These long chains of molecules that link up and create this kind of mesh within the material.
Yeah, and it's those polymers that are joining together. They're forming these connections, these bonds. And it's the type of bond that determines whether we're talking about a physical gel or a chemical gel.
Okay, so a stronger handshake, stronger gel.
That's a good way to put it.
Okay.
So physical gels are held together by weaker bonds. Like imagine holding hands with mittens on. It's pretty easy to break apart. So that's why you can, melt Jell-O with a little bit of heat.
Yeah.
But chemical gels, those are bonded together like a really, really tight hug. It's much more difficult to break those bonds.
Okay.
So like vulcanized rubber, that's an example of a chemical gel.
Gotcha. So we actually have a diagram here
Yeah.
from the textbook, figure 6.2, and it's really interesting. It shows all these different types of gelation transitions, almost like a roadmap,
Yeah.
different routes the material can take to become a gel. And I think one that you want to talk about was condensation polymerization.
Yeah, so condensation polymerization, that sounds kind of complicated, but it's actually simpler than it sounds. Essentially what's happening is you have these building blocks, and those are your monomers.
Okay.
And in condensation polymerization, these building blocks, they kind of snap together. And as they do, they release a little bit of water, and they form a longer chain. They form a polymer.
So like they're condensing, squeezing out the excess to create something bigger.
Yeah, you could put it that way. It's like, imagine you're building a Lego tower,
Okay.
and those Legos are thirsty.
All right. So the more connections, the stronger the gel.
Right, and it's not just about the number of connections, it's also about how they branch out.
Branching out. What are we talking about? Trees now? I thought we were talking about polymers.
Well, believe it or not, both. So
Right.
we've got these things called hyperbranched polymers. And so remember how we were talking about those Legos? So imagine those Legos, instead of just having two connecting points, they have way more.
Oh.
Like they got all these little arms sticking out. So they can connect in all sorts of directions.
Okay.
So you can get these really complex kind of tangled structures. And this branching is really important for gelation.
So the more tangled up those polymers get, the more likely they are to hold everything together in that gel structure.
Exactly. And remember how I was talking about those people holding hands in the room? As more and more people join hands, eventually you reach this point where everybody's connected and you get this giant network.
Yeah.
And that's the moment of gelation. That's when the magic happens.
Okay.
And it's all thanks to this concept called percolation.
Percolation. So like a coffee maker.
Kind of, yeah. It does involve a kind of flow, but instead of coffee, imagine like you've got a continent.
Okay.
And it's slowly being flooded by rain, right?
Okay.
So as the water level rises, all these like separate lakes, they start to merge together.
Okay.
And eventually they all connect, and suddenly, boom, you've got one giant ocean where there used to be land.
So the polymers are like the water, and as they're linking up, as they're branching out, they're essentially flooding the material.
That's a really good way to put it, yeah.
And then at a certain point, everything clicks into place, and you have a gel.
You're thinking like a polymer scientist now.
This is amazing.
And the cool thing about percolation is that it doesn't just apply to gels. I mean, you see it everywhere. Our sources talk about how, like, forest fires spread.
Wow.
Or, like, how diseases move through an orchard. It's all about these connections.
So the same principle that explains how Jell-O sets explains how a forest fire spreads.
In a way, yeah. It's about reaching this critical threshold.
It's like this hidden world of connections influencing everything around us.
That's a good way to put it, yeah.
That's really cool. So to get a closer look at those connections, let's zoom in on a very particular type of hyperbranched polymer. and that would be the dendrimer.
Dendrimers,
So
yep.
dendrimers, from what I understand, they're like imagine a perfectly symmetrical tree
Okay.
branching out in this really predictable pattern.
Yeah.
And that's kind of what a dendrimer is like, right?
Yeah. So they're built step by step, layer by layer,
Okay.
starting from a core molecule, and they branch out in this really controlled way.
So it's like a chemist is meticulously building this perfect polymer tree, branch by branch.
Yeah, and each layer that they add is called a generation.
Oh.
And you can imagine with each generation, the number of branches grows exponentially.
Right.
So you end up with these really, really complex structures.
So it's like a family tree on overdrive.
Exactly.
With each generation having tons of kids, and then those kids have even more kids, and so on and so on.
And all of those kids represent more connections, more bonds.
Which, it makes sense. The more branches you have, the more connections you can make.
Yeah.
And the more complex the dendrimer, the gel can become.
Right.
But something tells me that the real world of gels is not quite as neat and tidy as a perfectly grown dendrimer.
You're right about that. Yeah, they're kind of like the supermodels of the polymer world, you know? Very striking, very idealized,
Yeah.
but not exactly what you'd find if you walked out on the street.
So you're saying that real-life gels are more like the rest of us.
That's a good way to put it.
A little less symmetrical, a little less predictable.
Exactly. Yeah. In the real world, things aren't always so neat and tidy.
Right.
You have to factor in things like, impurities in the materials, little imperfections in the way that the polymers are formed.
Yeah.
Even just, the chaos of molecules bumping into each other during the reaction.
So if those perfectly grown dendrimers are like, I don't know, the carefully pruned bonsai trees of the gel world,
Okay.
real-life gels are more like the wild oak trees branching out every which way.
I like that analogy.
Yeah.
And just like, a wild oak is shaped by the wind and the rain. Real-world gels are shaped by all those imperfections and all those random events that we talked about.
Okay, so real-life gels are a little rough around the edges.
Yeah.
But does that even matter? I mean, does it change how they work?
It can. It can. I mean, think about it, a small defect in the structure of a gel
Yeah.
could make it weaker, more likely to break down.
Okay.
Or it could make it more flexible,
Oh.
able to adapt to different conditions. So these imperfections, they add a whole other layer of complexity to the world of gelation.
Right, and I think that's why we're going into all this detail, right?
Exactly.
It's not just about understanding gels in a textbook.
Yeah.
It's about understanding how they actually behave in the real world.
Exactly.
Yeah.
Yeah. And that's where things get really exciting.
Oh, yeah.
Because once you understand these fundamental principles of gelation, right.
And you start to see how those principles are affected by real-world conditions.
Okay.
That's when you can really start to design and create gels with very specific properties.
So it's like knowing the rules of the game lets you bend them to your advantage.
Exactly.
Okay.
And that brings us to the so what of all of this.
Yeah, I was wondering when we were going to get to that.
Right.
Why should we care? What's the bigger picture here?
Well, I mean, think about it. Gels are everywhere. I mean, we've been talking about Jell-O and hair gel.
Right.
But they're in our medicines, they're in our cosmetics.
Okay.
They're even in, high-tech materials like the things that are used in airplanes and smartphones.
Wait, seriously, there are gels in my smartphone.
Oh, yeah.
Wow.
And it's because, by understanding how to manipulate this process of gelation.
Right. Scientists and engineers can create materials with these really incredible properties.
Right.
Things that are stronger, more flexible, more biocompatible. I mean, the possibilities are really kind of endless.
That's pretty amazing. It's like this whole hidden world of gels is quietly holding together our modern lives.
Yeah, you could say that.
That's really cool.
Okay.
Before we get too carried away with all the amazing things that gels can do,
Sure.
let's just bring it back to the basics for a second.
Okay.
We talked about polymers and bonds and branching and percolation.
Right.
But let's just break it down to the simplest terms.
Yeah.
What at its core is gelation?
It's really about transformation. You're taking this loose collection of molecules, and suddenly they decide to get their act together and form something, more stable, more interconnected. It's like, imagine you're at a dance party.
Oh.
And at first, everybody's kind of doing their own thing, just individuals moving around.
Right.
And then suddenly, everybody links arms and starts moving together.
Okay, I like that visual.
Yeah, and that shift, that organization, that's really what gives gels these really unique properties.
So it's less about a liquid becoming a solid and more about it becoming, I don't know, organized.
You got it. Yeah, it's that organization that gives them, that jiggle, that ability to hold their shape, the
Right.
potential to be molded and manipulated.
So there's a whole lot more to gelation than meets the eye or the spoon, as the case may be.
Absolutely. And, we've only really scratched the surface here.
Oh, don't leave me hanging. What else is there?
Well, I mean, we've been talking a lot about the science, right? The how and the why of gelation.
Yeah,
But what about the art?
the art.
Yeah. Think about the culinary world for a second.
Okay.
I mean, chefs, they use gelation all the time
Oh, that's true. Yeah.
to craft these really exquisitely textured dishes,
Right.
your delicate panna cottas,
Yeah.
or those amazing savory aspects that you see at those fancy restaurants.
Yeah, they're manipulating gelation to create these culinary masterpieces.
Exactly.
Like the kitchen is their laboratory.
Yeah, in a way it is. I mean, they're experimenting with different ingredients, different temperatures, different techniques
Right.
to try to achieve a very specific texture, a very specific mouthfeel.
It's about pushing the boundaries of what gelation can do.
Yeah. Not just in a scientific sense, but in like a creative sense as well.
So it's like understanding the science of it is just the first step.
Yeah.
The real fun begins when we can actually start to play with it,
Totally, yeah.
experiment with it, see what we can create.
I hope that's what you take away from this deep dive.
Yeah.
Is that you don't just think of it as this scientific process, but like almost as a tool.
Okay.
Like a playground even.
I like it. Yeah.
And, who knows, maybe you'll be inspired to go and try some gelation experiments of your own in your own kitchen.
Well, I'm already thinking about some Jell-O molds, so challenge accepted. But on a serious note, this has been really fascinating.
Oh, good. I'm glad.
I mean, we've gone from Jell-O to dendrimers to culinary masterpieces,
So it's quite a journey, yeah?
all thanks to this seemingly simple process of methylation.
And the best part is, there's still so much more to explore.
Oh, yeah, I bet.
I mean, researchers are constantly making new discoveries about it, finding new applications,
Right.
pushing the boundaries of what these amazing materials can do.
It's like you open up one of those Russian nesting dolls, and just when you think you've gotten to the end, there's another layer, another surprise. Well, folks, there you have it.
There you have it.
A deep dive into the world of gelation. We hope you learned something new.
Absolutely.
Maybe even gained a whole new appreciation for the jiggly, gooey, sometimes surprisingly complex world of gels.
And hey, next time you see a gel, whether it's on your plate or in your smartphone, take a moment to think about all those molecules, doing their thing.
Yeah, doing their dance.
Exactly, because in the world of gelation, there's always more than meets the eye.
Always more.